This is Mr. Craig, and I am going to walk through a titration problem with you here. This type of question is very common on the AP exam whenever the titration question is asked. There's 4 parts to this question, and I'm going to break this video down into at least 3 parts. So the first part may not be as long, but parts C and D definitely will be. So when looking at the question here, here's our example question. We've got acetic acid, which is a weak acid, reacts with water according to the reaction represented above. Part A is asking for us to write the equilibrium expression for this reaction. So what we've done is we've written out our expression, and we want to make sure that we have our products over reactants. And you'll notice that in the balanced equation, which is above here, there's waters in the equation, but we never ever place a pure solid or a pure liquid in our equilibrium expression. That's why you don't see water anywhere in this expression here. We're going to use this expression at least one time, and then we'll use a variation of another expression here later on in the question. So part A, which is a very typical first equilibrium type question that's asked on the AP exam. Get it right, easy point, starting off. Part B, it's asking you we have a sample of acetic acids dissolved in water to produce 25 milliliters of a 0.01714 molar solution. It wants you to calculate the pH of this solution. Alright, so part B, since we have a volume and a molarity of our solution, we want to calculate the pH of this solution. We're going to go ahead and use a molar ice chart since we have nothing else other than acetic acid. Since acetic acid is a weak acid, it's a good idea to use an ice chart. The ice chart will help you organize your thoughts. It'll also help demonstrate who loses material while who gains material, so to speak. In other words, according to the balanced equation up above here, that's what we have in our top line of our ice chart here, that the acetic acid actually dissociates into the acetate ion, which is a common ion, and also behaves as a base, which is a conjugate ion of our acetic acid. Also, hydrogen is produced here, which is represented as H3O with a +1 charge, also known as hydronium. If you like showing just hydrogen there, then we would omit this column here, which is perfectly legal. You don't need to show the water in the ice chart. Also, one thing that you need to notice is that our initial concentrations for the acetate ion and for the hydronium are 0 in this part of the question. Since we are starting off and we know nothing about the acetate or the hydrogen concentration, it is 0. This will be the only time in the question that you have any concentration where you have no known amount. So we haven't actually started to dissociate the acetic acid. Within the ice chart, you have your letters ICE. Now, again, that's why we call it an ice chart, is because we're talking about our concentrations initially, our concentrations during the change, and then our concentrations at equilibrium. What you'll notice here is we have variables here, x, that we're using for the amount that is actually changing, and we have a plus x on this side and a minus x on the left side, or the reactant side. What we want to do is we want to calculate and see how much of the acetic acid actually dissociates into its common ion and hydrogen. And again, since this is a weak acid, not all of it is going to dissociate. Actually, a very small amount of it will dissociate. So, from our step in part A where we did our Ka, or our acid dissociation expression, we want to plug in the values for the acetate and for the hydronium ions, which are x. Each is x here. And then for the acetate, we have the 0.1714 minus x, because again, that's what we have in our value in the ice chart there. But you'll notice as we go from this step right here that has the minus x is taken away. This is known as the 5% rule. On every AP exam question, you may use the 5% rule. You do not need to use a quadratic equation, because the quadratic equation is not given on your equation sheet for the AP exam. Now, in college, you probably will have to do some problems where we use the quadratic equation, and in class we had to use the quadratic equation a couple times, but on the AP exam, time is of the essence, and they're looking for understanding rather than your math skills. So we're going to rearrange all the variables here so that we are down to this step here where we have x squared, which is our acetate and our hydronium concentration, is equal to 1.8 times 10 to the negative 5 times the concentration of the acetic acid. And what we did there was we actually took the 0.1714 and multiplied it on both sides, so we have the x squared all by itself. Once we multiply those two values together, then we come up with a 3.09 times 10 to the negative 6. We're trying to solve for x. So since we have x squared, we need to take the square root of that value to get our x value, which in this case is equal to our hydronium concentration, which is what we need to solve for the pH. So once you have your hydronium or hydrogen concentration, take the negative log of that value and you will come up with your desired pH for this part. And again, since it is a weak acid, we would expect the pH to be on the acidic side of the scale. Part C says the solution prepared in Part B is titrated with 0.2 molar sodium hydroxide. Calculate the pH of the solution when 5 milliliters of the base is added. At this point in the question, we do not know if we are at the equivalence point. So what we need to do is we need to do a calculation to see how many moles of the acetic acid or the weak acid we have and the number of moles of the sodium hydroxide we have, or the strong base. If those two numbers of moles are identical, we are at the equivalence point. If they are not the same, we are not at the equivalence point. That's a huge concept in titrations. Even more of an understanding is making sure that you realize that when you're doing a titration, you must convert your volumes and molarities into moles and compare the two. So what we need to do first of all is find out how many total moles of the acetic acid we have. So we're going to take our volume, 25 milliliters, multiply it times the molarity, which is 0.1714 molarity, to get our total number of moles, which in this case is 0.00429 moles of acetic acid. One very nice aspect of this question is that the number of moles of acetic acid will remain the same throughout the whole question. In other words, this will be the amount of acid that we place in the Erlenmeyer flask, and then we'll be titrating it with our sodium hydroxide or our strong base. So what we're going to do in this part is we're going to add 5 milliliters from the burette and find out how many total moles of the sodium hydroxide is going to be added to the 0.00429 moles of acetic acid. So we know the volume and we know the molarity of the sodium hydroxide. So in this case here, we're adding 0.001 moles of sodium hydroxide. So right off the bat, we can see that we are not at the equivalence point here. So what we need to do is we need to make our first ice chart. And our ice chart in this case for our titrations, once you are titrating a weak acid with a strong base or a strong acid with a weak base, you want to get your first ice chart to be a mole ice chart. One thing I want you to also notice is that the heading here is reversed from Part B. And what we have is our strong base, the hydroxide, on the product side, and we have our acetic acid on the product side, where the acetic acid was on the reactant side and the acetate ion was on the product side in the first part. We can show you that real quick. The reason why that was is because we had nothing but acetic acid that was dissociating the acetate ion and the hydrogen. Well, in this scenario, or this case here, we are adding a strong base, the hydroxide. So the hydroxide ions are influencing the acetic acid. What's going to happen is a hydrogen from the acetic acid is going to attach itself to the hydroxide to form water, and then what we're going to have left is the acetate ion. But what you do not want to do is have hydroxide on the reactant side, because when you go and write out your new Kb expression, you would have your hydroxide in the denominator, which is not a good scenario. We'll get there in a second. Alright, so what we want to do is we want to focus on the total number of moles that we just calculated up above and plug it into our ice chart. So our initial mole amounts for these are as listed. So we calculated the 0.00429 moles of the acetic acid, 0.001 moles of the hydroxide, And what I want you to notice is that we have approximately 0 on the acetate ion. There is a value for that from the previous step, but since we're using the 5% rule, go ahead and make that approximately 0. Yes, I know it's going to trouble some of you, but it's all right. Coming back over here, whichever two mole amounts, of the two mole amounts, whichever one's the least amount, that one will go to 0. We cannot have negative mole amounts. So whichever one's smaller goes to 0. Now, you'll notice here that the hydroxide actually is the smaller of the two amounts, so we're going to get exactly 0 hydroxide ions in the solution for a moment in time. But remember, this is an equilibrium problem, so equilibrium will be reestablished, and we'll have some concentration, because if we didn't have a concentration for the hydroxide, there's no way that you could calculate a pH or a pOH, which in this case we're going to calculate a pOH for. Alright, so now that we know how many moles we have after the two have mixed together, the hydroxide and the acetic acid, we need to find out what the concentrations of our acetic acid and our common ion, the acetate ion, happen to be. So again, since we're mixing two liquids together, we need to find out what the total volume of the solution is, because that changes our concentration. That's one reason why we never want to use molarities in a titration problem, because everything goes bad in that scenario. Find out moles. Alright, so the total number of milliliters that was added here, well, we had 25 mils of acetic acid, and it was added to 5 mils of, 5 mils of sodium hydroxide was added to the 25 mils of acetic acid, for a total volume in the flask of 30 milliliters. Be sure to convert those milliliters to liters, and then solve for the concentrations for each of the two things that remain, which is the acetic acid and the acetate ions. So we have our concentrations as listed here. Alright, now you'll notice that we have a Kb value here, and again I mentioned that earlier. The Kb value must be given if you have hydroxide, which we do in this scenario. So we want to take the Kw, which is equal to Ka times Kb, rearrange these variables so we get Kb all by itself, take the equilibrium constant, which is 1.0 times 10 to the negative 14, and divide it by the 1.8 times 10 to the negative 5. So here's our Kb value for this reaction. Alright, so now we have our molarity chart, and our ice chart. One thing you'll notice, since we're using the 5% rule, I tell my students only worry about the step at equilibrium. It doesn't make sense to go ahead and do a second complete ice chart when these concentrations are not going to change. Alright, so once we have our concentrations that we know about for at equilibrium, let's rearrange or write a new Kb expression, which we have yet to do. And again, it's products over reactants, and that's one reason why we want the hydroxide on top, is so that when we solve for the hydroxide, we don't have to do anything fancy to solve for this. Alright, solving for the hydroxide, here's our values that are given here, and now we can solve for the pH after we find the pOH. So in this case here, we have a concentration, we have a pH value of 4.23. Now, that should stand to make some sense here, that if we add a strong base, we would expect the pH to increase. Before we added any of the strong base, and it was just the acetic acid, we had a pH value of 2.76. So yes, that makes sense. The pH should go up, or should increase, if you add a strong base to the solution. I want to show a virtual titration here real quick, just to show how close we get to getting a pH of 4.23. Again, we're using a 5% rule, so I would hope that we get very, very close. In this demo here, I've got acetic acid, which is right here, and I've got my concentration. Things are a little bit scrunched up here, and I've got an exact concentration and an exact amount here. And then I'm going to use my sodium hydroxide, which I have my concentration of 0.2 and 50 milliliters. And then we need to use an appropriate indicator, and since we want our pH, when we get to the equivalence point, to be something else, the indicator really doesn't have any bearing on what we're doing at this moment here, so we'll pass on that for a moment. And then here's our burette. which is filled up with our sodium hydroxide. Within our Erlenmeyer flask here, we have our acetic acid, our 25 milliliters of that. And you'll notice that we start off with a pH of 2.76, which is pretty cool because that's what we calculated at the end of part B. Our pH was at 2.76. So we start off on a good note right off the bat here. Okay, and what's going to happen is once we start the titration here, you'll notice here that we have our initial volume, and that is of the sodium hydroxide within the burette. Current volume, since I haven't used any, is still 50, and then the amount of solution used. So what I want to do is try to go not too fast here and start titrating. So you'll see that we can see that the amount is being introduced into the Erlenmeyer flask, and as expected the pH is going up. Now I'm going to slow it down once we get very close to the 5 milliliters here. Let it run here, and we can go real fast or we can go real slow, so I don't want to go too fast here. Alright, so we're at 4, so I want to slow this baby down just a bit here. Okay, so, and the pH is increasing steadily. Hopefully this will get right at exactly 5 when we get there. Okay, we're 4.6 here. 4.7. Okay, try to slower down here. 4.8. And right there. Okay, 4.9. 4.99, and it says that our pH is 4.2. Even though our calculation says 4.23, that's pretty good considering that we've been using a 5% rule here. Also, we'll take a look at the titration curve as we go along. So we're not even close to the half equivalence point here, which is kind of neat. We'll come back to that here in a moment. All right, so continuing on with the next part here. Part D says calculate the pH at the equivalence point of the titration. Part C. So remember, at the equivalence point, the moles of the weak acid is equal to the moles of the strong base. The information that was given earlier, again, our moles of the acetic acid, like we said earlier, isn't changing throughout the whole problem. So at the equivalence point, if we have 0.00429 moles of acetic acid, then we are going to need the same exact number of moles of the sodium hydroxide. So one way that we're going to need to find out how much of the total volume of the sodium hydroxide added is to do a calculation. And in this case here, since we know the number of moles, 0.00429 moles of sodium hydroxide, and we know the concentration, we have to start with the number of moles so that the moles will cancel out, and then we'll be left with our volume, which in this case is our milliliters. So to have 0.00429 moles of the strong base added, I'm going to need 21.45 milliliters of sodium hydroxide added to the 25 milliliters of the acetic acid to reach the equivalence point. Now again, using our ice chart here, same format, we're going to start off with approximately 0. So this is acting like we're starting from a brand new titration. We're not going to have anything originally here, so we're going to start with just 25 milliliters in the Erlenmeyer flask, and then we're going to dump the 21.45 milliliters of the sodium hydroxide in there. So at the equivalence point, we're going to have the same number of moles of the acetic acid, same number of moles of the hydroxide. So both of these will go to exactly 0, and then equilibrium is going to be reestablished. So we're going to have the reduction of 0.00429 moles on the product side, but we're going to have the addition on the reactant side. So we only have a known constant or known mole amount for the common ion or the acetate. Alright, so we need to find out what the concentration of the acetate ion is so that we can find the pH, or actually the pOH, of the hydroxide. Before we can do that, we have to know what the total volume of our mixture is. So we know that we have 25 milliliters of our acetic acid, which is not going to change throughout this reaction, and then the 21.45 milliliters of the sodium hydroxide for a total volume of 46.45 milliliters. Convert that 46.45 milliliters into liters, so that we can get our new concentration. Now, in this ice chart, you'll notice that I have Y's in here. Now, I don't want you getting hung up and going, well, why are you using a Y now instead of an X? Well, it's just different, so it's okay. You use whatever variables you like. However, we're still going to use the 5% rule. And we're also still going to use the same KB value that we found in part C. So this part here I just stuck in there to remind you that we're still using the KB since we have hydroxide. Use your expression. In this case here, we do not know the concentration of the hydroxide. We do not know the concentration of the acetic acid, but we do know the concentration of the acetate ion. Rearrange the variables here, and that KB should say 5.5 times 10 to the negative 10. Excuse my error on that. We're going to solve for Y by using the 5% rule again. So get rid of the minus X and solve for Y. So now Y squared is equal to all of this. And then what we're going to do is we're going to take the square root of Y and get our concentration of hydroxide, also the concentration of acetic acid, but again, you can't find the pH from an acid. You have to find it from either hydrogen or hydroxide. So here's our concentration at the equivalence point. Let's quickly go to the demo. Now we already have 5 mils added in. Let's continue on here and add our 21.45. So I'm going pretty quickly here, and let's stop it for a moment here with 11 mils. And I want you to see that the pH has gone up a little bit. We're actually moving along on our titration curve here, so we'll keep adding our titrant here, which is our sodium hydroxide. Notice the pH is still slowly rising. As we get closer, I want to slow that down a little bit. Okay, so 18.9 there. Okay, so again, we're trying to get to 21.45, and notice that the pH will start taking off here. We have to be beyond our half equivalence point here, so it's right about there's our half equivalence point. So we'll continue on, and shortly you're going to start to notice the pH is going to start to change a little more quickly. So there's 18.7, okay, almost to 20 here, and 5.9. And we're still increasing. Alright, now we're getting to that 21. So let me stop it right about here. Take a look. Now we start to see that that curve is starting to go upward. That means we're very, very close to our equivalence point. So 21.45. And stop. Oh. Now that's kind of a pinkish color there. 21.45. If I go another drop there, it's going to really turn dark red. Boom. 21.45. So 9.8. Now let's look at our titration curve here, and let's finish this off real quickly. And you'll notice that the pH really peaks out there. Alright, so now we have our pH here where we want it around 8.86. Check the video real quick to see if we got close. We're running out of time.